Hello, everyone. Good evening and welcome to the Marshall W. Allworth Planetarium. My name is Jessica and I'm going to be your, tour guide to the bizarre universe this evening. You've also met Brayden and Ben, two of our students who are working and helping out this summer. So our show this evening is Beyond Bizarre, which is the strange and weird things that we found in the universe, or at least a few of them. There's a lot. Some of them, turns out we have figured out, but they're still really cool, so I wanted to include them. And some of them are still mysteries. Now, if at any time during the show you have any questions, feel free to just ask. I can't always see hands at the back, so you're welcome to just ask out loud. If you're not comfortable doing that, you can always come talk to me after the show if you have questions. Also, during the show, if you need to leave, you are welcome to do so at any time. You'll just exit through the same door you came in. Just, of course, be careful because it does get dark in here, but that's why we have the glow strips around the walls so that you can find your way out. And last little announcement thing, if you need the bathroom at any time, there are bathrooms down in the main building entrance right by the big telescope. I think that's all announcement type things, so I'm going to head to the back and we'll get started. Oh yeah, and I forgot to add, if the clouds are cooperating with us, we will also be doing a mini telescope viewing outside after the show as well. All right. Let's get in to Beyond Bizarre, Strange Things in Space. Now, we're going to be seeing lots of different strange and weird things. But we're going to start off with some things in our own solar system and then slowly move further and further out. So our first stop tonight is actually the planet Saturn. And we're going to be exploring the hexagon on Saturn. Now, Saturn is the second biggest planet in our solar system. But if we take a look at its north pole, we can see there's this weird hexagonal shaped storm swirling around the North Pole. And this hexagon is giant. Like one side of the hexagon is just a little bit bigger than the diameter of Earth. So it is gigantic. The winds in this storm are moving at speeds up to 200 miles per hour. And we don't quite understand how a storm of this shape forms. Circular storms, we know well. We see those on Earth in the forms of hurricanes. We see circular storms on Jupiter and Saturn and other planets as well. But a hexagon seems like something really weird to form naturally in a storm shape. But this is one mystery that we might kind of have solved. It turns out in the lab, if you play around with fluids, which gases are a fluid, if the fluids are moving at different speeds, they create these kind of vortices and eddies. And under the right conditions, in a lab, we have actually gotten these fluids to naturally form a hexagon based off of how the fluids moving at different speeds, how they interact and create these different eddies and vortices. It can naturally create this hexagon shape. In fact, in the lab, they were able to get many shapes, not just circles or hexagons. So it really seems like this could be the answer, that it's just the right wind speed. So this is the shape that we're getting out of the storm. But we don't know for sure yet that this is the answer. We also don't understand why only Saturn's North Pole has this and the South Pole doesn't. So starting to get there, starting to figure it out, but still some weirdness going on there. All right, for our next stop, we are going to head over to Jupiter and take a look at Jupiter's moon, Io. So this is Io in all its glory. Very interesting colors. We see yellows and oranges and reds and whites and blacks. What makes Io so interesting are all of these black spots that we're seeing. Those are volcanoes. Io has over 300 active volcanoes on its surface. It's so active that there are constantly eruptions and lava flows across the surface. We have caught, like you see in the middle image here, multiple times pictures of active eruptions happening. It is incredibly volcanically active, which in and of itself isn't weird, right? Earth has volcanoes. Venus has volcanoes. Mars has volcanoes. They're not active anymore, but it did used to have active volcanoes. So volcanoes in and of themselves aren't weird. What's weird is the fact that Io has them. You see, Io is about the same size as our moon. And our moon is not volcanically active because it's so small, it's cooled off by now. Everything when the solar system started was hot. But small things cool off faster than big things, which you know from life experience, right? So something like the moon is going to cool off a lot faster than, say, something the size of the Earth or bigger. So Io, being the same size, about the same size as our moon, should also have been cooled off. There should be no heat inside, and therefore nothing to drive all of this volcanic activity. So something has to be going on here making Io hot, because it should not be. Now, this is a mystery that we do have solved. And the culprits, oops, wrong button there. The culprits is Jupiter itself. You see, you have Jupiter on one side of Io, and it's constantly tugging Io towards it. And as it tugs Io, Io gets stretched out a little bit. And as it orbits Jupiter, how much it's being tugged changes. So sometimes it's being stretched out a lot, sometimes just a little bit. And so Io is constantly kind of flexing and relaxing. And as it does that, the interior rubs against itself. And just like you might do on a cool day to get your hands warm and you rub them together, as that interior rubs together, it heats up. And this is happening at such an extreme amount that it's creating a lot of heat. And this heat is what's driving the hundreds of active volcanoes that we find on Io, making it the most volcanically active object in our solar system. All right. Next up, we are going to head out of our solar system and go to a different planetary system. So we're heading over to a star system called 55 Cancri. That's the name of the star. And it has several planets around it, as you're seeing. But the one that we're particularly interested in is the planet 55 Cancri E. This one is one of the rare exoplanets or extrasolar planets that does have an actual name. It's named Janssen. So I'm going to refer to it as Janssen instead of 55 Cancri E because Janssen's just a lot easier for me to say. But this planet was the first ever super Earth that was found. So a super Earth is basically a planet that's rocky, but bigger than the Earth. So Jansen here is about twice the size of Earth and about 8 times the mass of the Earth. However, it is a lot closer to its star than our Earth is to our sun. Jansen here takes only 18 hours to complete one orbit around its star. So its year is 18 Earth hours long. It's so close to its star that the temperatures on the surface of this planet are incredibly hot. We're talking like almost 5,000 degrees Fahrenheit, which is why we hypothesize, as you're seeing here, that a lot of the surface must be molten rock. I do want to do a quick aside here. Unlike most of the things that we'll see in the planetarium that are real images, images of exoplanets like this are artistic interpretations of the data that we have. So this isn't what it actually looks like, it's what we think it looks like based off of the information we have. All right, so Jansen here, super Earth, really close to its star, making it really hot. Its surface is covered in molten rock, most likely, but that's not what makes this planet weird. You see, it being 8 times the mass of the Earth means there is a lot of stuff packed into a relatively small planet. It's only twice the size of Earth. That's going to create tremendous amounts of pressure. And based off of some of the information we have, we think that there is a high amount of carbon in this planet. Now, when you take carbon and you squeeze it under intense pressures, you get diamonds. So some models suggest that this planet may be about a third diamond, giving it its nickname of the Diamond Planet. Now, we don't know for sure. This is just one of the models that we have. We still need a lot of information to narrow this down and find out if it is actually a diamond planet. But even the possibility, I think, is really awesome, and it needed to be included in the show. So yeah, there you go, the Diamond Planet. All right, next up, we are going to head to a nebula. Now, a nebula is a gas cloud in space. And there are lots of them in our galaxy, lots of different types formed in lots of different ways. But the one we're going to be looking at is this one. It's known as the Red Rectangle Nebula. I'm sure you can guess why. Now, the Red Rectangle Nebula is what we call a planetary nebula. So this is what happens at the end of a small star's life, a star like our sun. But when this happens, and so we can take a look here, when a small star reaches the end of its life, it starts to puff up into what we call a red giant. And those outer layers eventually get so far out that they kind of just float away. So we get these layers of gas that are constantly kind of flowing out and away until you're left with just the dead core of the star at the center, which we call a white dwarf. And it's surrounded by all of this hot gas that was once part of the star. So I got a picture up on the left now. This is a typical planetary nebula. Usually, they look spherical, circular, because stars are circles. And if the gases are flowing out of it, the gas should come out in spheres as well. Even if they don't look like perfect circles and spheres, like here, you still see a lot of circularness to the structure. So the question with the Red Rectangle Nebula is how? how do you get something that should be circular and get this really nice rectangle shape out of it? We still haven't quite figured that one out. It is likely that there might be like a disc of stuff around the star that's maybe blocking things from going out in that direction, so they're pushed out from the top and bottom. But we're still trying to figure this out. So yeah, the Red Rectangle Nebula, the weirdly shaped gas cloud that we don't understand. All right. Our next stop is going to be to Omega Centauri. Now, I am baiting you a little bit with this title image here. This is the Milky Way galaxy, okay? Omega Centauri is what we refer to as a globular cluster. So a globular cluster is a group of stars. Globular clusters tend to have tens to hundreds of thousands of stars packed in real close together. And most globular clusters, like you're seeing here, are found around our Milky Way galaxy in what we refer to as the halo. Now, globular clusters in themselves have been really important for our understanding of how our galaxy formed, because the stars in globular clusters tend to be the oldest stars in our galaxy. So they are the first things that formed. So learning about them helps us learn about the early galaxy and what conditions were like. All right, so there's one globular cluster in particular that we're focusing on tonight, and that is the globular cluster. I start saying that too many times, it gets difficult. This is Omega Centauri. It is an absolutely gigantic globular cluster. To give you some comparisons here, Omega Centauri is in the top left. Other globular clusters are in the other three corners. When I said globular clusters typically have, tens to hundreds of thousands of stars, Omega Centauri has 10 million stars. And it's many times larger in size than the other globular clusters. So what's going on? What's going on here? We don't really, well, actually, no, I got ahead of myself. We do think we understand. We think that Omega Centauri here was actually once part of a dwarf galaxy that used to orbit around the Milky Way. You see, our Milky Way is surrounded not just by globular clusters, but also by small mini galaxies that we call dwarf galaxies. And you're seeing dwarf galaxies here in the red. But when those dwarf galaxies get too close to our Milky Way, the gravity of our galaxy can actually start to rip them apart. And that's what we're seeing here in these like streams of stars that we're seeing. Those are streams of stars from dwarf galaxies that were ripped apart because they got too close to our Milky Way. So we actually think that Omega Centauri did not start out as a globular cluster. It started out as a dwarf galaxy. And what we see now is what's left behind, that core of the galaxy that was able to hold itself together. And that's why it's so much bigger and has so many more stars than all of the other globular clusters that we see in our galaxy. So yeah, galactic cannibalism at its finest, right there. All right. It is time now to head out of our galaxy and take a look at some other galaxies. Now, in particular, we're going to look at something called Hoag's object. But to best understand it, you need a little bit of background on galaxy types. So generally, galaxies come in three main types. We have spiral disk galaxies, like our own Milky Way. We have elliptical galaxies, which tend to be more spherical or elliptical in shape. And then everything else is an irregular galaxy. So these are the things that, aren't spirals or ellipticals, okay? So now that we know what galaxies typically look like, let me show you Hoag's object. It looks a little funky. Now, when we first saw this galaxy, it didn't immediately raise red flags because we've seen things like this, like you're seeing here. This type of galaxy that we're seeing is actually an effect of something we call gravitational lensing. And I actually have a really great short little video that I think does a much better job of explaining it than I could. So I'm going to let this play, and then we'll talk a little bit more about Hoag's object. So here's a little bit of background on gravitational lensing.
Here at Sideshow Space, we sometimes talk about gravitational lensing when we talk about the discovery of new celestial objects. It's good and sciencey sounding. Gravitational lensing. But what does it actually mean? And how is it helping us find stuff? First, let's talk about what a lens is. Usually, it's a curved piece of glass or plastic that you find in a microscope, a telescope, or eyeglasses. It's curved so that the scattered light from whatever you're looking at gets focused onto a smaller area. Depending on the type of lens you're using, it can make things look bigger or make them look clearer and sharper. So now let's talk about gravity. Yes, it's the force that makes objects that have mass attract each other, but let's be a little more relativistic. Gravity is also the force that bends space-time. Massive objects create distortions in space the same way a paperweight creates a distortion if you put it on a bed sheet. Your mass is creating a dimple in space-time right now, and light, which has no mass, follows those distortions. If space is curved, light curves with it. So if a curved piece of glass can make a lens by bending the light that goes through it, why not a curved piece of space? Einstein first predicted gravitational lensing in 1912. 3 years before he published his work on the theory of relativity. It occurred to Einstein that if gravity bends space, it would also bend the light that was traveling through space. All you need to observe the phenomenon is a distant object that emits light, an observer, us, and something between us and that light source that's massive enough to act as a lens. 24 years went by before Einstein bothered to publish his prediction. He didn't think this was something we'd actually ever observe. But in 1979, telescopes were finally powerful enough to prove him right. The first effect of gravitational lensing we ever directly observed was Q0957-561, a double quasar that was actually only one quasar, but had two images in the sky, which seems crazy, but it's not. Think of normal glass lenses again. Yes, they make things look bigger and clearer, but what happens when they're out of focus? You start seeing double, and that's just because the light passing through the lens isn't converging perfectly on the other side. Instead of coming back together to create one nicely focused image, it creates two separate images of the same thing. Those two quasars were almost in focus. They look like they're about 6 seconds of arc apart, which is about the width of a CD or DVD viewed from 4 kilometers away. But between us and the quasar was a big elliptical galaxy that was serving as a lens, distorting the light just enough to create that double vision effect. In 1985, another type of gravitational lensing effect was seen for the first time. This was what astronomers named an Einstein cross, or 4 images of the same object arranged perpendicular to each other around the lens. The lens in this case was a galaxy that was distorting the light that passed around it and became known as Hooker's lens. And in 1988, astronomers observed the first Einstein ring. This is the beautiful effect you get when the light from an object is distorted into a halo, like what happens when you look at something through the base of a wine glass.
All right, so that's what we're seeing here. This is an Einstein ring, where we're seeing a galaxy that's behind this other galaxy, whose light is being kind of warped by that curvature of space-time, and it makes it look like it's a ring kind of bending around. But we know that this is actually a galaxy that's behind because in the light, we can actually figure out how far away a galaxy is. So based on the light, we know that this galaxy that looks like a ring here is actually much further away than the galaxy that's at the center. So let's go back to Hoag's object, because it does kind of look like an Einstein ring. The problem is the ring here is at the same distance as the central part, meaning this is not gravitational lensing. This is actually what the galaxy looks like. And it's what we now call a ring galaxy. And we don't know how these things form. What we do know is the center part must be a little bit older than the ring itself because the ring still looks blue. So it has really, really massive stars that have short lifetimes. So that ring must be younger for those blue stars to still be there. But how we get this nice, perfect ring around this central, what looks like an elliptical galaxy, we still haven't figured out. And since discovering Hoag's object, we have actually found a few other ring galaxies. They're very, very rare, which make it a little bit harder for us to study and learn more about because we just don't have a lot of data on them. But yeah, that is the very bizarre Hoag's object, teaching us that we definitely don't know everything about galaxies. There is still a lot of weird stuff out there. All right, our very last topic for tonight, and obviously something we have to talk about if we're talking about weird things in space, we're going to be talking about black holes. So, a black hole is essentially an object that has so much mass packed into such a small volume that it's gravity at the extreme. Now, black holes can form from the death of massive stars. When they go supernova, and most of the star gets exploded out, if the core, the center of the star that's left over is massive enough, it will actually collapse into itself, creating a black hole. Now, since gravity is at the extreme, what we mean by that is within the black hole, you cannot go fast enough to escape the pull of gravity. No matter how fast you go, that thing is going to pull you right back. Not even light can travel fast enough to escape from the gravitational pull, which is why they're black, because no light can come from them. The light we're seeing here is actually a disk of gas that's around the black hole that is shining. Now, black holes themselves get kind of a bad rep. They're not these cosmic vacuums. They don't just go around sucking everything up. You have to fall within the point of no return, or the event horizon. As long as you stay outside of that, you're fine. You're not going to get pulled in. You can go, you can escape from the gravity. It's once you cross that event horizon that things get too, extremed out, and you no longer have a choice. You are becoming a part of the black hole. Now, black holes come in different sizes. The one that we saw kind of the video of forming, this is what we would call a stellar mass black hole. So again, it's formed from the death of massive stars. And the black hole itself is really not that much bigger than Mars's moon Phobos. So it's about 25 kilometers in size. And typically has, less than 20 suns worth of material within it, which is kind of, it's crazy to think about, right? 20 suns packed into something the diameter of 25 kilometers, like that's crazy. Yeah, that's a stellar mass black hole. But there are bigger ones. There are what we call intermediate mass black holes. These tend to be in the thousands of suns worth of material, and they are smaller than the planet Jupiter. And then at the most extreme, we have the supermassive black hole, which contains at least 100,000 suns worth of material. But the object itself is actually smaller than the orbit of Mercury. So that's the event horizon size. Now, we have one of these monstrous supermassive black holes sitting at the center of our galaxy. It's called Sagittarius A star, and it contains about 4 million suns worth of material. Now, black holes themselves are weird because we don't understand what goes on inside of them. Our understanding of physics breaks down when we get to those extremes. But when we get to the supermassive black holes, we're even more baffled because we don't know how these things form. The initial thought was if you get a bunch of smaller black holes and they merge together, they'll eventually get bigger and bigger and bigger, and maybe you could build up to a supermassive black hole. The problem is we're finding supermassive black holes at the center of almost every galaxy. And we're seeing that they're formed really, really early on in the formation of galaxies, before there's enough time for them to grow out of smaller black holes. So there has to be something else going on. We don't know how these monsters form, and they are still a major mystery to astronomers. And as I said, we also still don't understand what goes on if you were to cross that event horizon and fall into the black hole. Now, in the math of black holes, you could possibly get on the other end kind of like a tunnel that connects to a theoretical object known as a white hole, which is basically the opposite of a black hole. Instead of pulling things in, it spews everything back out, which is where you get a lot of the sci-fi tropes of using black holes, or what we call wormholes here, using these to fast travel through the universe. But those are still just science fiction, at least for now. That is going to bring us to the end of our look at some of the strange things in space. As I said at the beginning, there are a lot more than this. This is some of my favorites and what we could fit into, about a 30-minute show here. So I'm going to get these lights up. Give me 1 second. I've been getting some messages, and I think it is about the telescope. All right, so looks like the telescope is out. Moon is a little low, but the telescope is out. If we want to go after we're done, try and take a look at the moon through the telescope. But before then, I just want to thank you so much for coming out tonight. See if there are any questions from anyone. Yes, at the front. What's the what? The very first one, we looked at something on Saturn. Yeah, it was pretty cool. Any other questions? All right, well, as I said, if you do have any questions, you just don't want to say them out loud, I will be back here, happy to answer and talk to anyone after the show. Thank you again so much for coming out. Before you head out at the main entrance by the big TV on that table, there are star charts, stickers, and other fun things that you are welcome to take with you. Brayden is outside with the telescope. We'll go see if there is anything seen out of it. And yeah, thank you again for coming out.